Good evening, everyone. Today we will be conducting our week 8 live session of the course Computational Fluid Dynamics. So, let's start with the questions. And while discussing the questions, whatever the concepts come up, we would discuss that separately. So, mm, so here we have a set of linear equations which is given by this ax plus b matrix. Matrix equation. So till now we have also discussed like different types of discretization, how we can convert a physical problem, like for example a conduction problem or a fluid flow problem, into discretized sets of equations. So there our objective was first to model the physical problem into differential equations that we have also done in like previous courses such as in fluid mechanics or heat transfer or chemical species transfer or whatever courses that you have done related to such transport phenomena in general. Uh, so there we uh, take a physical situation scenario and convert it into differential equations. And then we have seen methods like finite element method, finite difference method, finite volume method, and some other methods as well, where we take those differential equations and convert them into discretized algebraic equations where we are basically our unknowns are uh, let's say like some parameters like some velocity or temperature at particular discrete points and through set of algebraic equations we are trying to find out a solution for that. So it is definitely another step of approximation from the differential equations, but it reduces our computational like costs by a lot. Like it is sometimes even impossible to solve a generic differential equation to obtain an analytical solution of the differential equation. So we take we reduce it to algebraic equations, and that we have done. And after that, we have started seeing how we can solve such differential equations. So, uh, in the last live session, we started discussing about some iterative methods that we can use for solving this equation. So, namely like Jacobi and Gaussian. So, basically, now our objective has boiled down to solving this particular equation, ax plus b. So, what is this ax plus b? This A is a square matrix, x is the unknown, and b is another a vector, column vector, which is basically acts like the other source term or whatever extra like source term for our solute if we think in terms of finite volume method, source term and boundary conditions, those will go in this right hand side. So this is the way we are arranging this equation. And now our objective is to solve this. So we have seen that like basically the problem arises uh, that we have this equation and the solution will is basically A inverse B. But finding A inverse for a very large matrix is very difficult. We have to find the adjoint of the matrix and so on. So that is very difficult. So for that we take some alternative strategies. So one such strategy is the iterative methods, where what we do, we take a guess value. For example, x0 is a guess value, and then we see that x0 is actually not satisfying this particular equation. So we update our guess value uh, again to a better guess value in the next iteration step x1, and so on. We try and keep on updating and trying to converge into a solution like based on our previous guesses. We try to obtain a solution which approximately solves the set of linear equations. So that is an iterative approach. So one such approach is the Jacobi approach. So we have already discussed this, but let us do it again. So what is Jacobi approach? So let's say we have this initial guess x0. So we find x1 in such a way. So let's say, let me write down few equations, not in the matrix form, but the complete equation. So if I have, so this is one equation, this is my second equation, this is the third equation. Hmm. So what we would do is basically like arrange this in a certain way that it gives convergence and so on. So that we will discuss later. But let's say like this equation corresponds to the x1 variable. This equation corresponds to the x2 variable. This equation corresponds to the x3 variable. So this x2 we will separate from this the first equation. We will separate out x2. So from the first equation, x1, so we separate out x1, and everything else we take it on the other side. b1 minus a12 x2 minus a13 x3 divided by a11. So this we take onto the right hand side, and whatever the guess value we had, we would use that here x for x2 and x3. And if we put this value, we will get a new value for x1. And same thing we will do for x2 here, using the values of x10 and x30, we will find out some x21, and using the values of x10 and x20, we will find out some x31. So we get our next iteration, next guess, which is the collectively we can call it x1. So x superscript 1. So collectively we can call it this. And then so on we can get x2, x3, since till we get a desired accuracy. How we will get desired accuracy, that is we would come to that. Like basically if you put it in the equation, then it is like solving the left hand side is almost equal to the right hand side, or the values are not changing very much. X2, x3 are very close. So different kind of stock conditions we can use to see if you have attained the convergence. So this is a way, and this is the Jacobi method. What is the difference between Jacobi and Gauss-Seidel? In Gauss-Seidel, what we will do, since in the first equation only we have calculated a new value for x1, in the second equation we will use this new value. So instead of using x30 and x10, we will use x11. Then it becomes Gauss-Seidel. Okay. So this is Gauss-Seidel and Jacobi method. Create another slide. Yeah. So, uh, so let's try to write this whole thing in terms of this matrix form only. So what we do here is decompose this A into L, D, and U. So what is it like? So let's take an example of a 3 cross 3 matrix, like we have been doing so far. So A11, A12, A12, A21, A22, A23, A31, A32, A33. So this, if I write it like, This is our the decomposition that is talked about. So this is A, we know that. So this we can call L, or the lower triangular matrix. So you can see all values of in this lower triangle is conserved. So here we are not including the diagonal in the previously when we were talking about the Gauss elimination method and all, we were taking the diagonals when we are talking about lower triangular matrix. So Gauss elimination or LU decomposition, there we take the diagonals. But here we are not taking the diagonals because we are like writing this diagonal matrix as a separate one. So this is the D, and this is the most important one because like the updation is always done on this dmat these diagonal terms, and you will also see that the matrices which have a stronger diagonal terms, like the magnitude of the diagonal terms are much higher, they are much easier to solve using this Gauss-Seidel and Jacobi method. And this is similarly the upper triangle. Now, what happens in a Jacobi method? In a Jacobi method, we see that this x plus 1 is basically calculated from this diagonal matrix. So in the diagonal matrix, basically, when let me write it down more properly. So our matrix is AX. This has been decomposed into LX plus DX plus UX. Okay. So in Gauss-Seidel method, what we will do, we will try to find the new value of x. So xk plus 1 using the old values of x, which we would assign to these two. All the other values for each equation, all the non-diagonal terms will be multiplied with the previous guess value. So this is our Jacobi method. In Gauss-Seidel method, what would happen? Any equation which has been already previously solved will take the new value. So there, so this is Jacobi. Whereas if I write the same thing as Lk plus 1 dxk plus 1 plus uxk, then this becomes Gauss. Why you can see all the elements in the L, like if we are solving equations one by one, then L contains the coefficients of the terms which have already been calculated in a previous equation. So we have the updated value for all the variables which have the coefficients in the matrix L. Okay. So let's come to the question now. So can you tell me what is the value of this M and C? So basically we are writing this AX like this and putting it in the equation of AX plus B. So for Jacobi we will use this particular equation. So what does M and C come out to be? So we have this LXK plus DXK plus 1 plus UX is equal to B, right? So we can simply take all these xk terms in the right hand side, and k plus 1 would remain. So d xk plus 1 remains, and other than that we have b minus l x, sorry, not l, this is l plus u, l plus u x k. So if we just take d inverse, D inverse is very easy, right? What is D inverse? D inverse is basically like, since D is a diagonal matrix, all the terms, if individual terms reciprocals are taken, that itself is a inverse of a diagonal matrix. So unlike taking the inverse of the whole matrix A, taking inverse of D is pretty straightforward. So you can see what is the coefficient. So D inverse B is C, and minus D inverse L plus U, that is M. So this minus sign will be given. So this B is the correct. If there is any question, please like feel free to ask. If there is any difficult to understand any question, or if there is any question. Let's go to the next. So Jacobi method may be represented using this generic expression. So this expression is given, and we have like four statements. We have to uh, say which one is true and which one is false. So the first statement is given for spectral radius. So we must know what is a spectral radius. So can you tell me what is the spectral radius of like of a matrix? So spectral radius is basically like a measure of how much, like how quickly something might converge. So like to find out that, what we do is basically like we have to find out some the eigenvalues. So uh, so let's say like we want this particular equation, we are using this particular scheme, iterative scheme, and we want this to converge at a like some kth iteration. So for this convergence in kth iteration, we have what we would have is basically, uh, if I put some initial value, guess here. So let's see. Like in the first case, what would happen? X1 is equal to m x0 plus c. In the second case, it is x2 m x1 plus c. So let's take the difference between these. So x2 minus x1 is equal to m x1 minus x0. So this x2 minus x1 we can like take as a measurement of the error. So if this value becomes smaller and smaller, then the equation is convergent. So let's define this x1 minus x0 as e0, like error 0 kind of, and x2 minus x1 as error 1. So this is equal to. And now you can see very clearly, like if I want to find m e2, then I will have m multiplied with it, right? So if I just simply do this exercise again, then I will get e2 is equal to m e1, and if I substitute e1, then I will get m into e0. So for kth iteration, I will have mk All right. So these are actually like means these are vectors. So division will not really make any sense. But like try to imagine like a scalar of this. Like try to imagine this in terms of norms. That would be best. I can say. So if you take norms of all this, so you can see this ek by e0. You want this to decrease very fast, right? You want this to like decrease. You want this to be very small. So that would mean your error is getting less and less, and you are approaching closer to a solution. So what will be this measure will be equivalent to? This measure will be equivalent to some like uh, m to the power k's some norm, right? So this is basically related to your eigenvalue. Since we are like trying to calculate how fast something might converge, we take a conservative approach, and we say that this is related to a maximum eigenvalue. So the maximum magnitude of an eigenvalue is taken as a measure of how fast, how like quickly it will converge. So this itself is basically termed as spectral radius and like written as rho. So there may be other measures as well. Like we many a times actually finding eigenvalues is also very difficult. So many a times we just find the one norm and infinity norm. So one norm and infinity norm, is like the row norm and the column norm. Basically, you add up the absolute values of row and see which one is the maximum, and add up the absolute value of columns and see which one is maximum. So we take the one norm and infinity norm, and whichever is the like maximum out of this, we take that as our approximate spectral radius, and that itself like gives a sense of a magnitude of this matrix M. Any the reason for doing this like norms is basically to get a sense of the magnitude of a particular matrix, and that is provided well enough by this spectral radius. Hmm. So spectral radius, the convergence, spectral radius of convergence is related to maximum eigenvalue of the matrix. This is true. Hmm. This is related to the maximum eigenvalue of a matrix, spectral radius. And which matrix? In this case, it will depend on the M matrix. Note, it is not dependent on the A matrix. We are like basically whatever the method we are using, for that particular method, M will be different, and like we have just now calculated, M for Jacobi method is minus G inverse L plus U. However, for Gauss-Seidel method, it will not be the same expression. The expression will change. All. Uh, Second statement is uh, spectral radius of the convergence is related to minimum eigenvalue. This is not true. This is not. It is related to maximum eigenvalue. The sufficient condition for convergence is this greater than 1. What is this? This is nothing but a measure of spectral radius. Hmm. So this is an approximate measure of spectral radius. If you calculate the maximum magnitude of an eigenvalue, that is the like absolute definition of the spectral radius. However, an approximation for an approximation, we many times use this. So this norm row and norm column are nothing but the infinity and one norm respectively. So what should be this? Rho should be small, right? Rho should be small because rho is the measure of this E k by E0. So this should be small. And if this is less than 1, then only it is going towards any convergence. If it is more than 1, then obviously it is diverging. Your error is becoming larger and larger as your iteration goes on. So it should be less than 1. So your fourth statement must be correct. So in this case, 1 and 4 are correct. Is there any option for that? Yes. Okay. All right. Let's go to the next question. So consider 1D steady source free heat conduction in a rod. Let this system be discretized using finite volume. So in this context, consider the following statements. So this means so yeah. If the same heat flux is supplied at both boundaries, the Scarborough criteria is satisfied. Okay, so here we need to discuss what is the Scarborough criteria. So what is Scarborough criteria? It is also like related to whether some equation, this set of equations will converge on, and this is related to the Gauss Seidel method. So what does this says? This says basically, if I take the diagonal term and divide this diagonal term, and if I take the sum of like the neighboring terms of this particular diagonal. So this neighboring terms, why this neighboring terms concept is used is basically because like when you do this finite volume method and finite element methods, so these particular methods or finite difference method as well. These methods, they are generally diagonal centric methods. Like if you have a very large matrix, you would see only this diagonal and like the like a diagonal but a little off the diagonal basically. Yeah. So these particular elements have non-zero values. Other than that, the whole matrix is zero. Everything is zero. So it has another name. These are called sparse matrices. So sparse matrices has some have some properties, and we do exploit these properties to create faster and faster algorithms to find out the inverse of a matrix. So if you remember, our main aim is actually to find the inverse of the matrix, like to find the uh, best possible solution for x is equal to a inverse p. So that's what we are like trying to find. So Scarborough criteria takes advantage of that and like says that the neighbors, the neighbors of this particular uh, element, the absolute value of that this sum and this should be less than equal to 1. So what does this really mean? This means that our diagonal term must be large. Hmm. So basically, all summation of all the off diagonal terms, if I take, that should be either equal to or less than my diagonal term itself. So diagonal term should be larger than the all the off diagonal terms combined. So that is what is said. So along with this less than equal to, there is another condition applied which is one for at least one equation, and that is what this question is actually based on. So, so this particular condition arises for like physically satisfying a particular set of equations. So, if this is not true, all these particular equations have this one. So, what we would observe is like we do not get a physically consistent solution. So, what happens is if I have same heat flux supplied at both boundaries. So let's say we have this 1D conduction as like described here, and I have heat flux specified at both points. So Q double dash 1 and Q double dash. Now I want to find out the solution. So this like solution can be definitely found out, like we can apply boundary conditions here. Uh, Whatever the slope we will take, like k dt dx, we will equate it to q1, and here k dt dx we will equate to q1. So this we can do. We have already like covered finite volume method, but physically you can see that these two heat fluxes in the both the ends, they must be equal. Why? Because there is no energy storage which is happening inside this flow. So whatever heat is coming in must get out. So for any and it is also called a steady state. So if we means in steady state, whatever the heat flux is inside, from physically from our physical knowledge we can say whatever heat flux is going inside, it must also come out. So there is no rise in temperature. If there were some like inequality in the heat fluxes, then there will be a rise in temperature, and which will make the system unsteady. So in a steady state, definitely the flux going in will equate flux going. So what does this mean? This means that one of these boundary condition is not a boundary condition at all. If I simply say this is q1 double dash and not say this itself is like there is no additional information provided by this particular other boundary condition. So here, how many boundary conditions are effectively there? Only one boundary condition is there. So this is not a physically consistent problem. We must specify temperature at some end. At some point in this whole domain, we must specify a temperature from which, like using that as a reference, we can find out the other temperature. So, if we discretize this equation, like I will leave it to you. If there is any problem in discretizing this, then we can like say. Uh, so, finite volume we have already done. You can also refer to finite volume notes, how we can discretize this and like apply these boundary conditions. So so you will see after obtaining the equations, if you put the Scarborough criteria, where the same heat flux is applied at both ends, you would see this criteria is not satisfied. And particularly, this one for at least one equation, this particular criteria is not satisfied uh, when heat flux is specified at both points. However, when temperature is specified, what happens? If temperature is specified, this is now a physically consistent problem and it can be solved. And you will also see that this second condition is satisfied when the temperature is specified at one of the boundaries. So in this case, the Scarborough condition will also be satisfied. So in this case, Scarborough condition will be satisfied. In this case, Scarborough control criteria will not be satisfied. But in both the cases, the opposite statement is satisfied. So this will be none. So none of these two statements are correct. Both of these three statements say the opposite. Okay, let's go to the next question. All right. So we have discussed about our like spectral radius and so on, rate of convergence also a little bit we have discussed. So here they are asking for a like numerical problem kind of how many iterations will be required for solving a Gauss-Seidel problem. So for this we must know one expression. So the derivation of this expression, I think like in your class notes you will find. So I'm not going into the derivation in this like live session. So in the end, we would come to a result kind of in this way. So this is iterations. This is iteration number, and this is greater than our m. M is the order of accuracy. Like for example, if we want like up to 2 decimal places, then m will be 2. if you want up to 10 decimal places, then m is 10. So here it is like given as 5 decimal places, so m is 5. M is equal to 5, which is 6. So this is the accuracy that is required. So definitely you would expect if the accuracy is much higher. Higher accuracy means like more decimal places. So m will be larger. So if m is larger, then this number of iterations that will be required will also be larger. So logically it fits. And this is divided by the rate. So R, capital R here is the rate of convergence. So this rate of convergence is nothing but log 10 of 1 by rho. What is rho? Rho is the spectral radius. So if rho is large, if the spectral radius is large, then what would happen to this logarithm? Logarithm will be small. If yes, if rho is large, then the logarithm will be small, and that would lead to smaller rate of convergence. However, if rho is less small, then what would happen? Then this we would have a faster, higher rate of convergence, so a faster rate of convergence. So less iterations will be required if rho is low. So as when we are discussing the spectral radius, we already said that we take a conservative uh, estimate of rho. So whatever norms we calculate, whatever eigenvalues we calculate, we always take the maximum one as a spectral radius. So the reason it is taken so that we do not underestimate the number of iterations. So that is why this is taken. So that effect you can see here as well. So if rho is small, we would have a very high rate of convergence. But for a conservative approach, if rho is taken as the larger value, then we would get a rate of convergence as low, and thus number of iterations might be more number of iterations might be. So here we just have to put the values. So m is 5, and we have this log 10 1 by 0.8 is 0. Spectral radius is 0. So you can put it in your calculator and find out how much this is. Can someone tell me how much this value will be if you have a calculator nearby?
52.
Okay, 52. All right. So now, yeah, that is the number of iterations that will be required for Gauss sequence. What we would expect for Jacobi method? Jacobi method, we would expect larger number of iterations might be required. And how would that like what would be the difference between the estimation of Gauss seidel and Jacobi? The spectral radius. How? Because m will be different. So m value will be different. So your rho will be different, and so you will have a different minimum number of iterations. Let's go to the next one. Okay, we already know the Scarborough criteria. In this case, this is not a diagonal matrix, but no problem. We will take all the terms which are non-zero. Basically, all the terms. So we have to see whether this satisfies Scarborough criteria or not. So Scarborough criteria for this, like in the order given. So if it is in the order given, then this is the equation for x, this is the equation for y, this is the equation for z. So for x equations, we would take this 8 plus mod of minus 2, because we would take the neighbors of x. So those will be y and z, and divided by x, the coefficient of x. So all will be mod. So how much this is? This is 10 by 3. But we needed it to be less than 1, less than equal to 1 at least. But this is not the case. So we can clearly see that this does not satisfy the Scarborough criteria in the original form. So this is not. Okay. So the second statement is asking whether after reordering it satisfies the Scarborough criteria. So how would we reorder? We have to make it diagonally dominant. So here we can see like this 8 is the largest coefficient. So let's put it in the let's make it as a y equation. So let's make it y equation. Here similarly we will make it z equation because 4 is largest, and here x equation. Let's now calculate. So for this particular equation, how much is the value that is coming out to be? So this is 3 plus 2, 5 by 8. So this is definitely less than 1. So this is less than equal to 1. So the less than 1 criteria is also resolved. So we do not have to worry about that. Okay. What about this 1 plus 1 divided by 4? So this is 1. So this is 2 by 4. This is 2 by 4. What about the last equation? The last equation is 1 plus 2 divided by 5, which is 3 by 4. So very clearly, like we do not have to. The Scarborough criteria is now satisfied. So this is correct. The solution will converge using Gauss-Seidel method. So yes, that's what the Scarborough criteria like says. So we can be sure that it will converge with the Gauss-Seidel method. Okay. So which one is correct? Both 2 and 3. These are correct. Okay. Let's move to the next. So this is also the minimum number of iterations required for to achieve uh, 8 decimal places. So let's again write down the condition. So k will be greater than m divided by log base 10 of 1 by. So m is given, m is 8. But what is not given? Rho is not given. So we have to find out rho. And we are given that the like the method that will be used is Gauss-Seidel. So what we have to do? We have to find rho. We must first find out what is m. So the matrix we must first find out. So we would use that L plus U plus D method. Yeah. So in Gauss-Seidel, what happened? L already had the updated x value. So L already has the updated x values. D is updated x values we will calculate, and uh, U does not have updated x values, so it keeps the previous values which we used to find out the solution. So this is equal to B. So x k plus 1, this will be equal to minus L plus D inverse U xk plus B L plus D inverse. Okay, So this is very straightforward. What is the our M? M is minus L plus D inverse. Okay. So and also we have to here we have to rearrange this so that we get the diagonally dominant term. So this is the equation for y. You can see y is the largest. This is the equation for x, and this is the equation. Yeah. So I wrote the coefficient by mistake. So this is the equation for x. So can you try to find out the m? Can you try to find this matrix m? So we have to find L plus D uh, inverse, right? So what is L plus D? So the X matrix we will take first. So D will be like this is 5, Y is 10, and that is and L we would have here. So this is the Y equation's first coefficient, that is 1, and this is the first two coefficients of the Z equation, which is 2 and 3. So these are 0. So you have to find out the inverse, right? So one uh, thing about the inverse that you would all know is that like if I multiply it with the inverse, I should get the identity matrix. So you can use that trick to find out the inverse very like easily. Hmm. So for example, in this particular row, you know that this is the diagonal. So let's try to understand how we can find out this very easily. So this is our aim. We multiply it with something which gives the identity matrix. So you can see like this element is 1. So if I like how do I multiply matrices like this, right? So if I multiply this 5 with 1 by 5 and all then I will get this 1. Okay. What about the next element? For the next element, let's take this bottom element first. So sorry, let's take this element first. So for this element, I have to multiply this with the middle row, right? So and I will have to get 0. So uh, what should I multiply? Since I need to get 0, these two elements are 0. What multiplies with 5 is the first element. So this should be 0. Similarly, for this next one also, you can see that this should be 0, right? Whatever multiplies with the 5, that should be 0. So I got the first row. What about the second row? So second row, this first element, what I should get, I have already got this 1 by 5. So 1 into 1 by 5 is there, and but I need to get a 0. So 10 into something that like cancels out this 1 by 5. So what that would be? So if I multiply minus 1 by 50, if I multiply minus 1 by 50, then you can see 10 into minus 1 by 50 will give me minus 1 by 5, and that would cancel out with the same. So that is what is the element here. And similarly, you move to the next uh, uh, next term, and you see there is a 1 here. So mm, here you have to multiply this second row with the second column. So this is 0 and this is 0. So this becomes 1 by 10. And this third term you will see that this is 0, right? Because here you need to get 0, and you already have 0 into 1. So 10 should be multiplied by 0. So given this two, can you like find out this the third row? So it will there will be certain algebra, but you will be able to find out the third row as well. So this will be 1 by 10. This term you would need to calculate. These two terms you need to calculate. Please try to tell me how much this term will be. Okay. Does someone has some question? So why are we taking m is equal to 8? So the small m. So the small m is basically we have to achieve the 8 decimal place accuracy. So this just denotes the accuracy. So what is 8 decimal place accuracy? We mean that we must be accurate up to 8 decimal places after this like decimal point. We must be accurate up to 8 places. So up to 10 to the minus 8 we must be accurate. So that is uh, to achieve 8 decimal place accuracy. That is small m. Small m basically says that. So this is how you can calculate m, and what is basically required is the spectral radius of m. Uh, there is another way that you can do this very quick in a quicker way for this Gauss-Seidel method specifically is to use your this Scarborough criteria formula. So there what you do is basically add up all the non-diagonal elements and divide it with the diagonal element, right? And have this as less than 1. So where is the Scarborough criteria? Yeah, I have written it here. So in the Scarborough criteria, you see that term, this particular term is less than equal to 1. So what we can do is basically take our spectral radius to be equal to this. And this is much easier to calculate. Well, compared to taking this inverse of this m and doing the calculations. What I wanted to show you is that you would actually end up with a very similar value. And so you can do this exercise yourself. Try to find out m, the like this inverse of this. you have to find out L plus D and multiplied it with U, and then you have to find out the spectral radius of that. So spectral radius, for spectral radius, you can simply use that row norm and column norm, and whatever is the maximum of that, you can use that value. So you will see that this would come out to be very close to the whatever spectral value you are getting with this Scarborough criteria formula. So what is Scarborough criteria's formula for this y? This will be 1 plus 5 divided by 10. So the coefficient which multiplies with this y, since this is the y variables equation, so coefficient that is multiplied with the y would be in the denominator. Other all coefficients will be summed up in the numerator, the absolute value. So for this x, we will have 2 plus 2 divided by 5, and for this we will have 2 plus 3 divided by 10. So what are the values? So this is 0.6, this is 0.8, this is 0.5. What is the maximum of this? This is the maximum. So 0.8. So we can take our rho is equal to 0.8. And you can see like how easier this method is compared to like going through the route of calculating the exact value of the spectral radius. So we take simply take this as a spectral radius and calculate the problem. So you put m is equal to 8 here, 8, and you have to use your calculator. You can actually calculate the inverse of matrices also in your calculators if you have those 95 ES calculator, or like any similar kind of calculator. You can like calculate these inverses in your calculator. Can you tell me the value of this?
83.
83. Okay. All right. So 83, then 83 will be your minimum number of iterations. So if you have some decimal value, then what you would take? You would take the larger number. So if you have, let's say, instead of 83, if you had some value which is 82.1, you would not round it off to 82. You would take the larger number because the number of iterations you have, the minimum number of iterations cannot be 82 because it should be larger than this particular value. So if this value is coming out to be 82.1, you would report 83 as your minimum number. Okay. Does anyone have any question? Go to the next. Okay, try. Let's do one thing. Let's take a 2 minute break. Then we can like again continue from this particular question. You can try in the meanwhile if you want. I'm displaying the question here. All right. Let's restart. Anyone has any question? So can you explain why we took the value? Okay. Okay. Let's do that. So, what are you asking? Row value, right? The spectral radius. Hmm. So the spectral radius, like as we previously were saying, so basically the measure, so spectral radius is basically a measure of the magnitude of the this particular the matrix M. This particular matrix is uh, magnitude which signifies the convergence rate. So that is basically the spectral radius. So the convergence rate, we have this log base 10 1 by rho. We define this as our convergence rate in such a way that if like the rho value is high, we will have lower convergence rate. If rho value is low, we will have higher convergence. So, and if we like whether this uh, will converge or not, this particular set of this is the rate of convergence, but whether this will converge or not is basically rho should be less than 1 or less than equal to 1. Means it should be less than 1 for a like clear convergence, not less than equal to 1. It should be less than 1 because we discussed like rho is basically the measure of some the error at kth iteration divided by error at zeroth iteration. So we want like the error at a higher iteration number to be much smaller than compared to the error at the first iteration. So we want the error to decrease and decrease. So since rho is a measure of this, we want it to be less than 1. Okay. And now what we are saying here is we are basically using the result of the Scarborough uh, criteria. What is the criteria again? If I like just try to give it in this context, it is basically this AII mod. This is the diagonal term and summation of all mods of Aij when I is not equal to 0, which is all the off diagonal term. So this you take. So this should be less than equal to 1 for all rows, for all rows, and we should be less than 1 for at least one row. So this is our criteria. Now what we are doing here is basically we are comparing this with our spectral radius and seeing that there is a very similarity between this value and the spectral radius. So here what we basically did is just take the maximum of this particular value and define it as our spectral number. Because this is much easier to calculate, nothing else. So if we means to calculate our spectral number itself, we have to calculate these inverses and so on. That makes it much more tedious. Hmm. However, this is much easier to do, right? We simply sum the coefficients and divide it with the diagonal coefficient, and we will get our uh, spectral radius. So that is how we got point eight value. Okay, is it clear? If there's any difficulty, like any specific difficulty, you may ask. All right, there's Uh, we can, I think, proceed to the next question. But like, if you have any doubt, anytime you can. So here, what is basically given? We have. uh, linear system of size n, which means we have our matrix is n cross n. Matrix is n cross n. So, like the A matrix, the coefficient matrix will be n cross n size, and the ith eigenvalue of Jacobi iteration matrix n. So this is a iteration matrix. This is not A matrix, but its size will also be n cross n. Is given by this. Okay, so this is already given. So how many eigenvalues will be there? There will be n eigenvalues, right? Because this is an n-dimensional matrix. So this will vary from cos pi by n plus 1 to cos n pi n plus 1. Okay. So this will be the variation. It is given that for sufficiently large values of n, this is equal to this. Okay. If the size of the coefficient matrix change from 10 cross 10 to 100 cross 100, what would happen to the number of iterations required to achieve converged solution? So what is the number of iteration? Number of iterations we have seen that this is m by log 10 1 by rho. Now, when we are changing it from 10 cross 10 to 100 cross 100, what is actually happening? We are changing the spectral radius, because m is basically what we desire, the accuracy that we desire. That is not changing. We desire the same amount of accuracy, but like our matrix size has changed. So we have row 1 and row 2. So this is the number of iterations. So if I take the like ratio of number of iterations, so this will basically um, ratio of number of iterations, let's say R2 to R1. This will be equal to log base 10 1 by rho 1 divided by log base 10 1 by rho 2. So this like since this is reciprocal, then like we can simply have a minus sign outside, that would cancel out, and we can also change the like, base. So this becomes basically ln rho 1 divided by ln rho 2. Just like logarithm, uh, rules of logarithm we are applying, and we can get this. Okay, why ln? Because here this is given, so we can use. Okay, now eigenvalues. We come to the eigenvalues part. So eigenvalues here we have to like find out the eigenvalues, and whatever the maximum value of eigenvalue will be, that would be our spectral radius. This is the definition of spectral, right? So here we are given this cos value, and cos you can see this is between cos 0 and cos pi. So what? How does this? How does our like graph of cos look like between this? Hmm. So this will be like decrease means highest at 0, and again lowest on at pi, but the magnitude will be still be very close to 1. Hmm. Magnitude will be still very close to 1. This will be minus 1. This will be 1. So which value should we take for the maximum value? So you can actually see that the cos this and cos this, if I take the mod, these values are actually the same value. So we can take any of them. We can simply take, we can take the positive one, so that our calculation will be easy. So there only this particular thing comes into play. So cos, uh, this will be our rho. Let me write it in a different color. So rho is basically cos pi by n plus 1, which we are since this expression is given, we would use this minus pi square by 2n. Okay, but what we need? We need ln rho, right? Ln rho 1 and ln rho 2. So let's find ln rho. So it's basically log of this, which is minus pi square by 2n. So this becomes nothing but n2 square divided by n. So what is n2? N2 is 100, n1 is 10. So it's 100 square, which is 10 to the power 2 square, which is 10 to the power 4 by 10 square, which is this. So this is 100. So the number of iterations required is basically increasing by 100 times. So the number of iterations required is increasing by 100. This is our. Okay. Is there any question? I think someone has typed something. Okay. You can also like speak up, no problem. Because it is not possible for me to see the messages always. So, if you speak, it would be much more convenient to communicate that way. All right. So one, yes.
So in the previous question, why we are taking as increasing the hundred, sir?
Why we are taking increasing by 100? Uh,
100 times, sir.
why should we not like? Where is your doubt exactly? I'm not able to understand. So this is the expression for our iterations, right? This is fine, right?
Yes, sir.
Hmm.
Yes, sir.
So if I am just simply like taking the ratio between these two.
Okay, sir.
So if I am taking the ratio, number of iterations, if I am taking the ratio and I got 100. So I am seeing that the number of iterations is required just 100 times. So this is my k, number of iterations. What I'm basically doing is I'm doing k2 by k1, right?
Yes, sir. Yes, sir.
Okay. So this if I get 100, then definitely I will like my k2 will be is 100 times of k1. All right. So consider the system of equations ax plus b. Okay. So now we are moving to our new topic. So we were discussing Gauss-Seidel and Jacobi iterations so far, and now we will move to gradient descent. So what is this? This is also basically an iterative method to calculate our like solve this particular system of equations Ax plus b. That is which is our main aim. So what do we do in this particular method? Uh, we basically define a function which is like a potential function, and we try to minimize this function. What is the speciality of this function? If you simply take gradient of this function, so this is half x transpose ax. So if like if it is in this form x transpose x, and we have to take uh, like the derivative of this, this is treated like an x square. So you can break this and also see, but like eventually it will come out to be x square. So this particular things boils down to 2a into x. So these two will be cancelled. So x transpose x, this behaves like an x square in a matrix operation. We can use that, or you can like break it up and like calculate as well. Like for your own satisfaction, you can do that. So and this b x transpose is there. If I take a derivative, the x will be gone b, and c is a constant, so definitely b mm, uh, is, that will be 0. So what we get is basically x minus b. So if we equate this to 0, if we equate our gradient of x to 0, then x minus b is equal to 0, or ax is equal to 0. Ax is equal to b. So we will get the equation that we wanted to solve. So what we have to do is basically find grad f is equal to 0. And what does grad f equal to 0 means? It means that it is a in minima. It could have been maxima as well, but like if you see, like mm, if you take this expression and then you try to like find out what are the neighboring values, like you are taking this f at a certain x, but you are let's say moving by epsilon, moving by a certain epsilon, and you try to calculate this. You will put x instead of x, you will put x plus epsilon, and what you will see is basically this like it can be proved. You can do this. I think it is also like done in the lecture. So this will always come to be greater than f of x. If this is the case, then you can definitely say that if grad f is equal to 0 for this particular form of functions, then this is a minima. So what we have to find out is a minima. So we have a like a multivariable function here because x is basically multivariable. It's a vector. It has a lot of variables, and we are defining a potential function from there, and we would be approaching to a particular point where this function is minimum. So which of these particular statements are correct about gradient descent method? So gradient search method uh, may be useful if A is symmetric and positive. So this is the case. This is true. So if A is symmetric and positive definite, only then these particular methods are useful. Otherwise, uh, these gradient based methods are like will not give you accurate solution. Okay. What about the second question? For application of such method, one defines the following function. This function. Yes. So this is the function. So this is also correct. Grad f is equal to 0 is equivalent to ax is equal to b. That's what we discussed just now. Grad f is equal to 0 would give us ax is equal to b. What is this? That is the solution. So that's why we are searching for a mean. Okay. And the last statement is therefore maximization of f gives the solution. That would have been true if this particular statement wouldn't be there. But this is like this can be proved. Like if you like simply put x plus epsilon instead of x in this particular equation, then you would automatically come up with a form in which like you can if a is positive definite, definitely this symmetric and positive definite, these two conditions you will have to use, then uh, then like f of x has to be a minima. Any f of x plus epsilon is greater than f of x. So this last statement is false in this case. So what are the correct answers? 1, 2, and 3. So here this will be minimum. All right. So consider the system Ax is equal to B. A and B are given, and we have to use the steepest descent method with an initial guess which is given. Then what is the form of x at the end of the first iteration? So we must know how this particular steepest descent method is uh, carried out. So here basically we have to find out f, that is f we would have to find out anyways. So f is the form of f is transpose a x minus b x transpose plus c. All right. So this is the form of f. Initial guess value is given. The initial guess value, if we put, we would get a particular value of f, and uh, then in the steepest descent method, what we would do is basically like find uh, like uh, in this particular initial guess, we will have a particular f value, and this would give us a particular curve in a three-dimensional plane. So here there are two variables, so we will get a contour. So we will get a contour, and let's say the minimum point is this. So and we lie somewhere in this contour. What we would take? We would take the normal descent here and go a particular distance, and then again we like take a particular value of f. We would get a contour, and we again take the the perpendicular distance towards this minimum point, and go a particular distance and repeat this process. Okay. Uh, so the steps that we can we follow for this can, is first we find out if this is x0. So we take this as x0. This is the initial guess. So from here we will first find out a residual r0. What is r0? R0 is basically ax0 minus b. This should be 0 if uh, x0 were the perfect solution. But x0 is an approximation, so r0 will not be 0. And this is what we have to measure basically. R0 is the magnitude, the norms of R0 should decrease, and at a particular time, if it decreases below a threshold value, we would say the system of linear equations has been solved. So R0 value we have to calculate, and then we would estimate the value by which we would update our x0. So the new value x1 will be the old value plus this r0. This r0 is basically like giving us uh, like uh, the distance, the vector which is from the solution. So ax minus b, this is 0 when the solution has been reached. So the solution point, if we take that as our reference point, so from there, whatever the point we are in currently, this is our R0. And what we will have is basically x0 is the x1 is the next point, and we will have some alpha 0 value, by which this particular next point would come towards this uh, our solution. So that is the main aim. So how to find the alpha 0? Alpha 0 using the steepest descent method, this alpha 0 expression looks like this: R0 transpose by R0, R0 transpose A R0. So this you have to calculate. So let's do that. Let's first calculate R0. R0 is nothing but minus B, because x0 is 0 comma 0, 0 0. So this is minus 1 minus 1. R0 we have calculated. So now we have to calculate alpha 0. So alpha 0 is minus 1 minus 1. This is minus 1 minus 1. Minus 1 minus 1. This is 1 0 0 2 and minus 1. So what is the numerator? Numerator is 1 plus 1, which is 2. What about the denominator? Denominator, let's calculate this, do this first multiplication. So if we do this, this is minus 1 and minus 2, right? So minus 1 into minus 1, and this is 0, and minus 1 into 0 and minus 1 into minus 2. So this is minus 1 minus 2. And if I like do the next multiplication with minus 1 minus 2, then this is 1 plus 2. What is this? This is 1 by 3. Okay, so we got the value of alpha 0, we got the value of R0. We can calculate this. How much is this? X0 is 0. So we simply have to bother about this. So this is minus 1 by 3 minus 1. I think I have done some like mistake in sign. Can you check if there is any mistake in any algebra? Please check if there is any mistake in the algebra. There is no option as such here.
Sir, alpha naught is coming out to be 2 by 3 now.
Oh, it is coming out to be 2 by 3. Yes, yes.
2 by 3.
Oh, that is correct. This is true here. This is true. Okay. So uh, this is 2 by 3. Then also there is some mistake in sign, I guess. Somewhere I have done some mistake in sign. Mm, okay, I will not be able to get it right now. It's not coming to me. If you can catch let me know if there is any mistake. It is telling that this is positive sign, so must have missed out something. Okay, let's go to the next question for right now. So this is a much more straightforward question. This is like fx is equal to 0. We have to find out what does it represent. So fx we already know. Uh, what is the expression of x transpose A x minus B uh, dx transpose plus c is equal to, and this we have to put equal to 0. So initial guess is taken as uh, 0 comma 0. So we would do that. Let's first try to calculate this function. So, so this is half x transpose is x1 x2. This is 1 0 0 1. This is the identity matrix, so that will be very easy for our calculation. Minus b is 1 1. X transpose is, it should be the opposite way. This is x1 x2, and this is 1 1 plus c equal to 0. So we can simply write it out as half. This is since this is identity matrix, we can simply multiply this two. This is x1 square plus x2 minus x1 minus x2. This is equal to okay, this c is there, plus c. This is equal to c. Now, why this initial guess is given now must be very clear to you. We have to find out the value of c, because c we can choose anything, right? C is in our hand. So initial guess is, if it is 0 comma 0, it must satisfy this equation. So if you put 0 comma 0 here, you will see like all the terms vanish. Like this is 0, this is 0, every term is vanishing. So c must be equal to 0. So c is 0. C is 0 from this initial guess. We are putting this initial guess, and it must satisfy this equation to the C. Okay. Now what does this represent? Let us write it in a better form. So x1 square minus 2x1 plus x2 square minus 2x2. This is equal to C. So what we can do is simply like add a 1 here, add a 1 here, and add 2. What does this give us? This gives us x1 minus 1 whole square plus x2 minus 1 whole square is equal to 2. So what is this? This is basically equation of a circle whose center is 1 comma 1 and radius is root 2, right? So this particular option will be correct. All right. So these were the questions that I had for discussion today. Might which problem? Yes, this problem that we have. Please check. Like I think this might be a mistake. If this is sign is minus, then I think our problem is. Please check whether this is the correct expression or not. That might be the problem. I think that is itself the problem. So this sign might be minus. Okay, check it from your class notes or like from in the any book that you are reading. This sign might be minus. All right. So Is there any question related to whatever we discussed today or any of the previous sessions? If there are no questions, then I will close the session. Thank you.